What type of financial considerations do you need to make if you want to buy something expensive, like a car? How much money do you have? How much money can you borrow? The cost of borrowing money, like time and interest on a loan. What model? Number of seats? Fuel mileage? Do you buy used or new? What are the maintenance costs? What's the useful lifetime of the car? How long will you own it? And do you plan to sell it afterwards? These are the same types of considerations you need to apply in engineering economics when deciding between different treatment technologies. Following this module, you will be able to understand the difference between capital and operating costs, be able to calculate costs of two equivalent technologies with annualized capital and operating costs, and explain how to include resource recovery into engineering economics. Capital costs are fixed, one-time expenses incurred on the purchase of land, buildings, construction, and equipment used. So, for example, if you wanted to build a treatment plant, it would include the cost of the property and the construction of the entire facility. But with sanitation, it also includes the infrastructure to get wastewater or fecal sludge to the treatment plant, because there's no point in having a treatment plant without a way to get the wastewater there. Operating costs are the expenses which are related to the operation of a business or equipment or treatment facility. With fecal sludge management, this could be collection and transport businesses, vacuum trucks, treatment facilities, or the operations budget of a utility. It is the cost of resources just to maintain their existence. Net operating costs can be offset by revenues, such as the sale of treatment end products. If we think about the wide range of fecal sludge treatment technologies that are available and covered in other modules, it is already apparent that they will all have very different costs of construction or capital costs, but also different operating costs based on the complexity of operation. In addition, they're going to have very different lifetimes. For example, comparing infrastructure costs for how many years will a vacuum truck work, compare that to, say, what is the operational lifetime of a sewer. For example, the Cloaca Maxima drainage system in Rome is still operating after 2,500 years. It's like comparing apples and oranges. When costs and benefits differ over time between different options, we need to apply equivalent equations for the comparison of the relative economic value. To achieve this, we can apply concepts like annualized costs. If we know the capital cost, operating cost, service lifetime, and real interest rate, we can use this equation to compare the relative equivalent costs of two different technologies. As an example, I will walk you through the case study presented in this paper, comparing existing side-by-side sewer and fecal sludge management systems in Dakar, Senegal. First, let's compare both of the process flows. For the sewer-based system, there are sewer lines and pumping stations, followed by a wastewater treatment plant. The process flow has screening and grit removal, primary settling, activated sludge, clarifiers, with the effluent going to tertiary treatment with some water reclamation at a neighboring golf course and the remainder discharged to ocean. The solids go to anaerobic digestion with some of the remaining solids sold to public works for use in greenways. The fecal sludge management chain has septic tanks with vacuum trucks for collection and transport, with settling tanks followed by drying beds. The effluent from both the settling and drying beds goes to the activated sludge treatment in the wastewater treatment chain, and the solids from the drying beds are also used in greenways. These are the stakeholders and financial flows that we considered in the evaluation. With the sewer-based system, we start at the household-level user who pays a sanitation tax to ONAS. ONAS is the National Sanitation Utility. The sanitation tax is included as a drinking water tariff to fund the sewer-based wastewater treatment infrastructure. The end user of the reclaimed water and the treated sludge also pays a fee to ONAS for those products. With the fecal sludge management chain, again starting with the household level user, they have to pay for construction of their septic tank. They still pay the sanitation tax because it's incorporated in the drinking water tariff, even though they're not using the sewer. They also then pay emptying services from a collection and transport company. The collection and transport company then pays an unloading fee to ONAS when they discharge the fecal sludge at the treatment plant. And again, the end users are paying ONAS for the resource recovery products. All of the calculations, data, and assumptions we used are included in the supplemental information of the paper from this spreadsheet. For all calculations, a real interest rate of 5% was assumed for the lending interest rate, adjusted for inflation based on values used by the World Bank. To estimate annualized capital costs for the sewer-based system, we first had to assume lifetimes. For the household connection, we selected 20 years. For the sewer, we used a relatively conservative estimate based on PVC construction of 30 years, also 30 years for the pumping station and treatment plant. Then we needed to determine total capital costs. These information were obtained from ONAS directly from their operating information. Then we had to derive a number for the number of household sewer connections. This was based on the original number, the number of people per household, the growth rate, to determine a per capita value. We then used the annualized cost equation to determine annualized capital values. In addition, we have itemization of annual operating costs, which are also provided in the supplemental information. We then did similar calculations for the fecal sludge management system, where first we had to assume lifetimes, here 50 years for a septic tank, 15 years for an emptying truck, and 30 years for the treatment plant. Then we have total capital costs for the septic tanks, vacuum trucks, and for the treatment plant. Again, then we have the number of per capita people that are served by the system. We then annualized these capital values and itemized annual operating costs, also presented in the supplemental information. This table from the paper summarizes the results. What we see is with the capital costs, the sewer-based system compared to the fecal sludge management system is 10 times more expensive. And with operating costs evaluated annually, 1.5 times more expensive. So the overall sewer-based system for both capital and annual operating costs was 5 times more expensive. What else we see from the results is that with the sewer-based system, the costs are mainly borne by ONAS, whereas in the fecal sludge management service chain, the costs are much more spread out among the stakeholders. It is also important to note that this is not equitable, as poor households in the fecal sludge management system are having to pay twice for sanitation. Once with a sewer tariff included in their drinking water, and second when they are paying for fecal sludge management services. This is where it is also interesting to think about how resource recovery options could offset costs. In this model, resource recovery is generating almost no income. What if we could find an option to get $10 for a truckload of 5 cubic meters of fecal sludge? And in Dakar, they have 2.2 million cubic meters of fecal sludge produced per year. That would work out as an annualized cost of 8.8 per capita net operating gain, because it is something that could be brought in each year to offset operating costs. This could have a significant effect on the financial balance of the fecal sludge management system, making it close to a net zero total cost. Could this be used to reduce the financial burden to poor households? This is where reorganizing financial flows and thinking about business models comes into play. When applying this type of analysis, you also need to consider other complexities like inflation, taxes, depreciation, economy of scale, and salvage value, and also conduct a sensitivity analysis to evaluate the effect of any assumptions you made. In addition, this example was based on the assumption that both systems are providing the same level of public and environmental health protection. This module provided an introduction of one type of equivalent equation method that can be used to compare costs. There are also many others, like net present value. These type of calculations are also further complicated with fecal sludge management because many technologies that we want to compare have not yet been implemented, so we don't have experience on which to base estimated capital and operating costs, and so we need to make a series of assumptions. These estimates will continue to improve with increased implementations. So, like making a decision about which car to buy, it's not purely about the cost. You also have to include economic analysis with other variables in a design approach, like environmental and social impacts, local laws and regulations, and regional economic development. In conclusion, in this module, you learn the difference between capital and operating costs, how to calculate the equivalent cost of two different types of systems, and consider how to include resource recovery into the analysis. Thanks for joining. See you next time.